Welcome back to part 2 of the short introduction into the calculator portion of the numerical approximator. In the last video we went over the root finding methods such as bisection and Newton's method, and today we're going to start off with the integration method. So the integration method simply performs an adaptive composite Simpson's rule on single integration method with a given function with bounds, and they can be called with the two following ways. You can either integrate with two bounds, a to b, or you can integrate from a to infinity. So here I'm going to give a basic example of integrating the following function, cosine of x plus 1 over x, which has the following value. We can say integrate cosine of x plus x raised to the negative 1 power. Integrate from 1 to 10, let's say, has the following value. And here I'm going to go to Symbolab, which is an online calculator, and here it performs the integral for us, and we have 0.91709 as we can see here. And we can also integrate values to infinity, so we can say infinity, or actually plug this in, we can go to 0. However, if we're going to do this, we need a function that is not divergent, so we can say 1 over x squared plus 4. That would give the following value, and we can say integrate 1 divided by parentheses x squared plus 4 from 0 to infinity. I think I'm going to go back to the documentation. So it's infty. We get 0.785, which is exactly what we find here. So now that finishes up all the functions in our calculator. Now I'm going to move on to the matrix algebra portion of the calculator. So now I'm going to clear our workspace. We can go here to Edit, Clear Workspace. And so now how would you actually insert a matrix into our calculator? Simply, you can make one from scratch as such. You can say 3, 4, 5. This would be the first row. First row has 3 columns, 1, 5, 6. And then close it off. And then here we have a simple matrix. We can assign this, so if I also press the up arrow, we can go to our previous commands. And so we can say x is now equal to this. So we can click here on x. X is a matrix. It is a 2 by 3 matrix. We can get the transpose of a matrix. So transpose of x. We can store that in y. So now y is a 3 by 2. And now we can perform matrix multiplication. So x times y, as we can see here, which should return a 3 by 3 matrix. As we can see, we can go back and we can also multiply a constant, so 3 times this would be this times 3. We can take the square root of y times x, which takes the square root of every value. And so this works with any types of values. If we want to multiply constants, subtract it from constants, and such. So now we can actually import a data set. So we're going to call this iris. We're going to import the iris data set. So here's the iris data set. It is a 150 by 4 matrix. Here we have RStudio again, and I already have a variable named data, which contains the iris data set. Head of data simply shows the first 6 columns, first 6 rows, as we can see here. And so now what we can do here is we can actually index through our matrices. So we can say iris at 0, 0 to get the 0, 0 value. We can also iterate through columns and through rows. So if I wanted to get all the columns of a matrix and only the first row, I would say 0, colon, and that would return all the columns and all the rows. We can say I want the first 5 rows, first 6 rows, because this is 0 indexed, and all the columns, we can see here, which just returns the head as well. So now what we can do is we can also say iris of all the rows up to the 5th row, and all the columns between 4 and 5. So out of bounds, we can go here to 3, out of bounds again. Let's make this 3 and let's make this 2. There we have it. So the first 5 rows, first 6 rows only containing columns 2 and 3. And so now I'm going to go over some basic statistical frameworks. So we can say we have our iris data set, as we can see here. I wanted to get the mean of the iris data set, which simply takes each column and calculates the mean. So this is the mean of each column. We can also take the variance of the data set. So this is the variance of each column. We could also take the sum of each column if that would make sense in your particular data set. So this is the sum. And what we can do here is we can also take the covariance matrix. So we can say covariance of iris. This is the covariance matrix, which simply has the covariance terms on the non-diagonals and the variance terms on the diagonals. We can compare that with the covariance matrix found in R. As we can see here, 0.68, 0.68, negative 0.04, negative 0.039, 1.27, 1.27. So as you can see here, we're extremely accurate in calculating our covariance matrix. And there are different ways to actually calculate the covariance matrix. Some people divide by n, some people divide by n-1, or even n-2. So these slight differences between our two covariance matrices simply could be because we're calculating them different using a different equation. We can also calculate the correlation matrix. So here are the correlation matrix. We can do this as well in R. So here on the non-diagonals, we have a correlation matrices such as 0.817, 0.817, 0.8717, 0.8717, and such. And so now what I'm going to do is I'm going to go over some basic static functions that we can do. So all the functions we've gone over in the previous the previous tutorial and this tutorial is that you can actually use these inside of other functions. So we can actually say y times x, which returns a 3 by 3. We can times the correlation of iris times the covariance of iris. So as we can see here, each of these return their own matrices values, and we can calculate them as such. However, these static functions, they do not return any type of value. So I'm going to first go here back to iris. What we can do here is we can actually get row. So we can say get row of iris, get 3. So this will return the third row. And we can also get column of iris. Now these are not static functions. I just wanted to show them real quick before we go over. So the static functions we can go here to is delete row and set row. So I can actually set row of iris. If I was to go back here to the documentation, set row takes a matrix integer value. So I can make our own row from scratch as 0, 0, 0, 0. And let's make it the fourth row. So success, if I print out iris now, the fourth row is all zeros, as we can see here, which is exactly what we did. And now let's say we can delete row of iris 4. We go back, oops, I deleted the wrong one. So there we have it, our rows of zeros is now gone. And now let's assign this back to our iris data set. So now we have a 148 by 4 matrix because we deleted 2 rows. So now I'm going to go over some of the systems of linear equations solutions, such as LU and QR. But before I do that, I forgot to mention the z-score method. So we can calculate the z-scores of iris, as we can see here. And I can simply do the head of the scale. The scale method is the equivalent in R of our data. So 0.897, 0.918. As we can see here, this is probably going to be different because we deleted 2 complete rows, which is going to change the mean and the variance. But however, we can see that they're extremely similar in nature. So I'm going to now go over the LU function, which simply decomposes our matrix into 2 equivalent matrices, an upper triangular matrix U and a lower triangular matrix L. So here we have this, error, LU function must be given a square matrix. So now we can say we can store our covariance in a variable named cov, take the LU of cov. So here we have our lower triangular matrix and our upper triangular matrix. And if you want to get these values, simply use the $ symbol, which simply means obtain. So we can obtain the L, we can obtain the U, as we can see here. And what we can do is L times LU of cov U, which simply means our L times U, which should equal our covariance, our original covariance, as we can see here. And we can also use the LU to solve a system of linear equations. So our covariance is a 4x4 matrix. Now we need to get a B matrix from our data set. We can go from, let's say, 0 to 3 to get 4 rows, and let's get it from column 2. So here's our B. We can say LU of covariance B, and it returns the solution. So what it simply does is we have our covariance. We can treat this as a system of linear equations, so x1, x2, x3, x4, x1, x2, x3, x4, and it would be this equals 1.4. So solve for our system of linear equations, and this would be our solution. So we can actually get this value and store it in a variable named sol. So we can see here is covariance times our sol should equal B as such. We can do the same thing for QR. So the QR uses the Gram-Schmidt orthogonalization method. So we can say covariance, where Q is an orthogonal matrix and R is an upper triangular matrix. And if you want to obtain the values, it'll be the same. So it would be Q, R, multiply those together, you're going to get your original matrix of cov. And what you can also do is you can get the solution. So we can say cov of B, and it returns our solution matrix, as we can see. So the LU and the QR both return the exact same solution matrices. What you can also do is find the inverse of a matrix using the inverse function. So inverse requires a symmetric matrix, so the inverse of the covariance is as follows. And the equivalent function in R is solve, so we can solve for the covariance of our data. And here we have 10.314, 10.26, negative 6.713, negative 6.716. Now this is going to be different simply because our covariance matrix is built off our iris data set, which is missing 2 complete rows. So that's why there's a little bit of a difference. We can also do is find the eigenvalues and eigenvectors of a matrix using the eigen function. So eigen requires a symmetric matrix, eigen of cov. Here we have the values and the vectors, and you can simply obtain these using the same format, $values to get the values. If you want to get the vectors, you can do that as well using the $obtain vectors. So unfortunately, this is all the time we have left for today, but in the next video, we're going to be finishing up all the functions given for matrix algebra.